Let's take a look at section 6.1. We're going to be solving systems of linear equations. This time we're going to be using matrices to do that. Now, you'll remember from a previous section, we saw systems of linear equations. And a system of linear equations is two or more linear equations that are solved simultaneously. We're looking for the point that's a common solution to both equations. Graphically, it's the point that is the intersection of the two lines. So, for example, let's say we have the system of equations 2x plus 3y equals to negative 13, and x plus 4y is equal to negative 14. Now, whenever you're solving a system of equations, you've seen that all we really do is either add or multiply. What we can do is we can take a row and multiply it by a certain number. We can say, oh, we're going to multiply this bottom row by 2. Or we're going to multiply the bottom row by negative 2. Or we're going to multiply the top row by 1/2. Or we're going to multiply the top row by negative 4/3. Or whatever. So one thing we can do is we can take an entire row and multiply it times a number. Another thing we can do is we can add rows together. After all, we saw that as the addition method for solving systems of linear equations. Finally, the last thing we can do, which we never really did much of, but we could switch these two rows. Here, we could take this top equation, write it on the bottom, and it wouldn't matter. We'd still have the same two equations, which means we'd still be solving the same system. So those three things are things that we can commonly do whenever we're solving a system of equations using the addition method. The substitution method is different, but for now, let's talk about the addition method. Now, one thing to note is that as long as these are lined up, meaning as long as this first set of terms involves the variable x, and as long as these involve the variable y, and as long as these are just regular numbers, notice that it doesn't really matter that we have the letters here. For example, if I were to add straight up and down, 2x plus 1x is 3x, but the x doesn't really play a role. All I really paid attention to was the 2 and the 1. If I were to multiply the top row by 3, well, that would give me 6x plus 9y is equal to negative 39. But notice the x and the y didn't do anything. All we handled were the numbers. So we can write this same system of equations a different way. This is called an augmented matrix. So what we're going to do is we're going to write down the coefficients without the variables. Now, we're going to do it in the same order. So here, 2x plus 3y equals negative 13. I'm going to write this as a 2. I'm going to leave some space. I'm going to write that as a 3. I'm going to leave some space. And then I'm going to write minus 13. The second equation, 1x plus 4y equals negative 14. There's a 1 there. There's a 4 there. And there's a minus 14 here. In a way, this is like synthetic division, in that we're ignoring the stuff that's redundant or the stuff that's unnecessary for the momentary computation to make things a little bit simpler to write down. Now, here, you notice there's a difference between these numbers and these numbers. These are the coefficients of some variable expressions, whereas these are just constant numbers. Here, we're going to put a line right here, and this line sort of helps to keep track of where the equal sign was. Now, to keep all of these numbers together, and because we're going to be using other numbers alongside of these, we're going to put this together in a set of brackets. This system right here has now become this set of numbers inside these brackets. This is called a matrix. Whenever you have a matrix like this, where you have a line that separates another set of numbers on this side, again, that's what represents the equal sign, this is called the augmented column of the matrix. So here we go. This is a matrix. Whenever you have this extra set of numbers on this side, this is called the augmented column. And so this kind of matrix is called an augmented matrix. Okay? Now, every matrix is organized in rows. These are the rows. This is row number 1, and this is row number 2. If we had any more rows, we would go 3, 4, 5. The rows are labeled from top to bottom. So top row is the first one, bottom row is the second one. If there were any more, you'd have the third, the fourth, and the fifth. These are called columns. You see the word column. And those are labeled from left to right. So this is column number 1. This is column number 2. And this one would be column number 3. Just like that. All right? Now, these rows, each row represents one equation. Well, we just said that there were 3 things we could do to the equations of a system of equations. We can either multiply them all by a number, we can add the 2 lines together, or we can switch the 2 rows. So those 2 rows, those 2 equations, don't leave us with a lot of options. And since we don't have a lot of options, well, that's a good thing. There's not too many things that we can do here. So these are called row operations. The row operations are the things that you're allowed to do to the rows of your matrix. Notice they're not called column operations. We're not going to have any of those. These are things that you can do to a row. There's nothing you should do to a column, only to a row. The 3 basic row operations, we've already seen them, but let's go ahead and say them again. The first row operation is you are allowed to switch any 2 rows. If you want this row on the bottom and this one on top, that's fine. You can just switch them. You can switch any 2 rows. The second thing you can do is you can take any row and multiply it by any constant number except for 0. And say, well, why not 0? Well, because if you use 0, if you multiply this by 0, you get 0, 0, and 0. 0 plus 0 is equal to 0, which is true, but then all of a sudden your information's gone. You don't have anything left to help you solve your equation. So here you can multiply any row by any non-zero constant. And the third thing you can do is you can add any 2 rows together. This is basically the addition method, but done without the variables. All right, so if those are our row operations, those are what we can do. What are we trying to get? Well, we're trying to get the solutions to our system. Well, okay, but how do I know when I get those? What am I doing with this matrix to get a result? Well, the goal is we're trying to get a matrix that's in row echelon form. That's in what now? All right, so let's define what we mean by a row echelon form. If you have a matrix in row echelon form, it satisfies 3 conditions. First of all, if there are any rows that are made up of all zeros, those should always be on the very bottom. Any rows of zeros are on the bottom. For our example here, we won't have any rows of zeros, but in some bigger examples you will. So the next condition that we have is that the leading term, the leading number, going from left to right, of each row should be the number 1. So here you see the very first number in this row is the number 2. We don't want that. We want the very first number in each row to be the number 1. So here, the lead number, I guess I should say the lead non-zero number. The lead non-zero number of each row is the number 1. And the third condition is that the lead non-zero number of each row should be to the right of the one above it. The lead non-zero number of a column. No, sorry. These should be rows. We're only talking about row operations. The lead non-zero number of a row should be to the right of the lead non-zero row of the row immediately above. Now that might sound a little confusing, but essentially all we're saying is, okay, if there's any row that's all zeros, put that on the bottom. You can do that by switching rows. That's one of our operations. The next thing we want to do is we want to make sure that this first number, if it's a zero, well then it's a zero. We go on to the next one. But if it's not a zero, it should be the number 1. And now, this one, the front number should also be the number 1. Oh, but it shouldn't be here. It should be, if this one was the first number that was not 0 in this row, the first non-zero number of the next row should be over here. It should move over to the right by 1. So what you have is you end up having the 1s in a diagonal pattern. This should be a 1. This should be a 1. So row echelon form will end up looking something like this, where you're going to have a 1 right here, and then these are going to be some numbers. And here I'm going to assume that I have a much bigger matrix than the one I have up here, just so we can see the pattern a little better. All right, so now, and then here's my augmented column, and then there's my other number. All right, now, here, this should be a 0, because the first number that's not 0 should be to the right of this one. Okay, so then that would be this point. That would be this at this spot. Okay, but now the first number should be a 1. And then everything after that is just some number. We don't know what that is, and we're not going to worry about that right now. Now over here, we also want the first non-zero number to be the number 1. But that first non-zero number should be to the right of this spot. Okay, well that's this one right here. Well, that means that all the numbers in front of that were zeros. So in row echelon form really means you want 1s along the diagonals, and all the stuff in front of the 1s should be zeros. All the stuff behind the 1s, well, those are just going to be some numbers that we'll see as we go through. All right? So this is called row echelon form. Now, row echelon form, let's go ahead and label that. There is a little bit more specific version of row echelon form called reduced row echelon form. It's almost exactly the same as this one, but with one extra condition. This is reduced row echelon. And it has the extra condition that all numbers in the matrix above a leading 1, in other words, in front of above these numbers right here, above these 1s, should be 0. All right? So reduced row echelon form, okay, you'd have 1s right here in the diagonals, zeros would be in front, but now everything above the 1s, well, here there's nothing above this one, so we don't worry about that. Everything above the 1s should also be zeros. So really you just have 1s along the diagonals and zeros everywhere else. These over here are just whatever numbers. If you have any rows that are all zeros, those should be on the very, very bottom. 0, 0, 0, 0. All right? But we're not going to see that too much. But if there are any rows that have all zeros, those should go on the bottom after everything else. So these, either row echelon or reduced row echelon, will be our goals. Whenever we have a matrix, to use the matrix to solve the system that that matrix represents, we're going to put that system into one of these two forms. Depending on which form we put it in, we have a different name for that procedure. The procedures are very, very similar, and in fact, even their names are similar, but they are just a little different. So let's go ahead. I'm going to copy this down right here. This is the system. 2x plus 3y equals negative 13. X plus 4y equals negative 14. And the augmented matrix that represents that system of equations, I'm going to copy that down as well. Okay. Now, I want to get this into row echelon form. And saying, what about reduced row echelon form? We'll get to that in a second. Let's do row echelon first. When we're using the row echelon form of a matrix to solve, this is called the Gaussian elimination method. All right, so we want to use our row operations. Remember what those are. We can switch rows, we can multiply rows by a non-zero constant, or we can add rows together. And the goal is to get a 1 right here and a 0 below that. To get a 1 right here, and then we're done. Now, the nice thing about this is that as long as you use those 3 row operations, and only those 3 row operations, you can never really be wrong. It might take you 3 steps to finish this problem. It might take me 5 steps to finish this problem, and it might take someone else 7 steps to finish the problem. But as long as all of us used only these kinds of row operations, we will all get the exact same answer. So as long as you don't give up, and as long as you don't use something other than one of these 3 row operations, you can't be wrong. But, well, sometimes it can take a little long. So here, I'm going to show you one way to use Gaussian elimination to solve this system. Note that there are 100 other ways you might do this using the same 3 row operations. The goal is to get a 1 here, a 1 here, and a 0 underneath this 1. Which steps you take in what order, those are kind of up to you. So first of all, I noticed that I want this to be the number 1, and this is already the number 1. Well, you know what? I'm allowed to switch rows. So I'm going to go ahead and switch those 2 rows. So I'm going to take the bottom row and put it on the top. And I'm going to take the top row and put it on the bottom. All right, that was nice and simple. That is now the number 1. That's exactly what I wanted it to be. I wanted it to be the number 1. But now, I want everything below it to be the number 0. You note that depending on the size of your matrix and on exactly what numbers you have, this could take several steps. What you want to do is you want to record what steps you're going to take. So here, between these 2 steps, I have switched row number 1 with row number 2. I'm going to make a little notation in between these. I'm going to write row number 1, I'm going to write row number 2, and I'm going to put a little double-sided arrow. This does a couple of things. 1, it records what you just did. And 2, it tells everyone else what you just did. So if there's a mistake, we can go back and figure out, okay, here's what you did. Okay, yeah, that was right. Okay, here's your next step. Okay, that's right. Okay, here's your next step. Oh, that was where the problem was. So it's a good way for you to double check your work and see exactly what the steps you took were. The other thing is being a little more pragmatic. I have to grade your work, right? Your homework, your exams, and so forth. And being able to see what steps you took are going to show me exactly what you meant to do. That way, if you did it right, well, then you did it right. And if you didn't do it right, well, then you at least knew what you were supposed to do, even if there was a mistake in there. That whole showing your work kind of thing. So to show that you switched 2 rows, what you do is you draw the 2 rows that you switched with a little arrow in between them. All right, so now the next thing I want to do is I want to take this number and turn it into a 0. All right, well, notice if I take this top row and I multiply it by a -2, that would be -2, and then these would be other numbers. But notice, if that's a -2, I could add these 2 rows together, and 2 plus -2 would be 0. So what I want to do is I want to take this row, multiply it by a -2, and then add it to this row. Here's how I'm going to record that process. I'm going to take -2 times row number 1. That would turn that to a -2. And now I'm going to add that to row number 2. That result is going to become the new row number 2. I'm going to change this bottom row. So here I'm going to draw a little arrow, and I'm going to write row number 2. That tells me that whatever this result is, it's going to become row number 2. It's going to sit at the bottom. Here, -2 times row number 1. Well, let's see what that would look like. Let me do some work on the side here. If I multiply each of these numbers times -2, well, that's going to be -2 times 1, that's -2 times 4, and that's -2 times -14. But now I'm going to add whatever's in the bottom row. So I'm going to add 2. Here I'm going to add 3. And here I'm going to add negative 13. So here that's negative 2 plus 2. Well, that's 0. That's going to be negative 8 plus 3. That's negative 5. And that's going to be positive 28 minus 13. That's going to be 15. So now that becomes the new bottom row. So now this is 1, 4, negative 14. This bottom row is now 0, negative 5, and 15. All right. So now that's the number 1. And below it I have a 0. Now this is the first non-zero number in this row. But remember, the first non-zero number is not supposed to be negative 5 or positive 5 or any other number except for 1. So now the next step is to change this to the number 1. Well, notice if I just take this and multiply by negative 1 over 5, the negative times the negative will be a positive. 1/5 times 5 is the number 1. So I'm going to take negative 1/5 and multiply it times my bottom row. Negative 1/5 times row 2. And once I do that, that's going to become my new row number 2. Notice, here's what I'm starting with. Here's what I'm doing to it. And then here's what it's going to replace. So let me do that off to the side. I'm going to take negative 1/5 times the first number. It's going to be negative 1/5 times the second number. And negative 1/5 times the third number. And so that's 0, that's 1, and that's negative 3. So now that's going to be 1, 4, negative 14. That's going to be 0, 1, and negative 3. This is now in row echelon form. There's a 1 along the diagonal, and below that there's a 0. With the Gaussian elimination method, that's it. You're done. You say, okay, so now what do I do? Well, now, remember, these rows represent the equations of a system. 2x plus 3y equals negative 13. 1x plus 4y equals negative 14. Well, these will also represent an equation. This would be 1x. So here, let's change this back into a system. This would be 1x plus 4y equals negative 14. This would be no x. Okay, so I'm not going to bother writing an x. That would be 1y equals negative 3. Oh, but notice, I know what y is. Y is equal to negative 3. Oh, but since I know what y is, I could plug that in right here. And that would now be x plus 4 times negative 3 is equal to negative 14. This is called back substituting. Literally, you find the bottom number and substitute backwards into the next equation. All right? This is the last step of Gaussian elimination. You're going to take the y that you found, plug it in here, and now that's x plus negative 12. Well, let me just write that as x minus 12 equals to negative 14. And if I add 12 to both sides, I get x equals to negative 2. And putting that together, that's the solution to my system. Negative 2, comma, negative 3. Just like that. All right? Now, this might seem like a long procedure, but that might just be because I talk too much. Yeah? There's a lot of explanation that goes into saying what each of these row operations are. This procedure isn't quite that long, though. Let's do another example and see what it looks like without having all the extra exposition. So let's take a look at an example. We're going to solve the system, and here we're going to use Gaussian elimination. Solve by Gaussian elimination. And our system is going to be negative 3, x plus 11y. That's equal to 58. And x minus 3y. That's equal to negative 16. All right. So now we want to change this into a matrix. Negative 3, 11, 58, 1 minus 3 minus 16. Just like that. So now we want to change this to be the number 1. You'll notice there's a 1 right here, so switching these two rows would be a quick way to do that. If I take row number 1 and I switch it with row number 2, the top row is now 1 minus 3 minus 16, and the bottom row is now minus 3, 11, and 58. Okay, so now that's the number 1. What we want to do now is change anything that's below it to be the number 0. The simplest way to do that is usually going to be multiply this by whatever number it takes to be the opposite of this, and then add. I say usually because sometimes that'll lead you to some unpleasant numbers over here, but usually it'll work out fairly nicely. So here I'm going to take this top row, and if I just triple that, row number 1 times 3, that will be 3, which if I add to negative 3 will give me 0. So take the top row times 3, and I'm going to add the second row, and that's going to become my new second row. So let me go and do that off to the side. I'm going to take 3 times the 1. I'm going to take 3 times the negative 3, and 3 times the negative 16. And I'm going to add to that this very bottom row, which is negative 3, 11, and 58. And if I do that, that's going to give me 0. That's negative 9 plus 11 is 2. And here that's negative 48 plus 58 is 10. So that becomes my bottom row. So that's going to be 1 minus 3 and minus 16. That hasn't changed. But my bottom row is now 0, 2, and 10. Just like that. And now we're almost done. That's a 1, and below it's a 0. I want that to be a 1. Okay, so let's divide this whole row by 2. That way 2 divided by 2 is 1. If you have a number that you want to change to a 0, usually what you want to do is you want to add copies of the number 1 that's above it. If you want to change something to a number 1, usually you're going to multiply or divide to get that to be the number 1. To make zeros, you're adding and subtracting. To make ones, you're multiplying and dividing. So here, let me go ahead and multiply this bottom row by 1/2. And that's going to become my new bottom row. So let's see here. That's 1/2 times 0, 1/2 times 2, and 1/2 times 10. And that becomes my new bottom row. So that's 1 minus 3 minus 16. The bottom row is now, well, that's half of 0 is 0, half of 2 is 1, and half of 10 is 5. And there we go. This is now in row echelon form, which means we're done reducing our matrix. And now, to finish off the Gaussian elimination method, we're going to go ahead and back substitute. This top line represents x minus 3y equals minus 16. This bottom row represents, well, that's nothing, so let's ignore that. That's y equals 5. But now, since we know y is equal to 5, we can substitute that up here, and that's going to give us x minus 3 times 5 equals negative 16. Well, negative 3 times 5 is negative 15, like that. And now if I just add the 15 over to the other side, add 15 there, add 15 there, I get x is equal to negative 1. And there we go. Y is 5, x is negative 1. So my solution is negative 1, comma 5. That's the point where the graphs of these two equations would cross. That's the solution that solves both equations. Now let's take a look at one more. Let's say we're going to solve the system that's given by 2x plus 4y equals to 14. And we're going to take 5x minus 2y equals negative 25. Okay? So we could change this into a matrix and start reducing. I want you to pause the video and give that a try. I want you to change this into a matrix with the augmented column, and then reduce it so that it's in row echelon form. But before you start back substituting, before you start solving for the equation, go ahead and stop. Leave it as a matrix in row echelon form. All right, and once you're there, go ahead and unpause the video. All right, so let's see what we have here. Now remember, there are different ways of reducing your matrix. So if the steps that I take are a little different from the ones you take, that's going to be okay. As long as you follow the same 3 row operations, that is switching rows, multiplying rows by a constant number other than 0, and adding rows together. As long as that's all you did, you can't be wrong. All right, so here we go. We're going to go ahead and convert this to a matrix. This should look the same for everyone, even if the rest of it doesn't. So this will look like this, where these numbers are in the augmented column and all the rest are over here. Now we want to change this to a 1 and below it into zeros. Now here I don't have the option of switching these because that's not the number 1 either. But what I can do is I can just cut this top row in half. That'll be nice. I can take row number 1 and multiply it by a half. And that will become my new row number 1. So take all the elements of row number 1, take all of the numbers in row number 1. Notice I said the word elements. That's what you call the numbers in the matrix. We're going to talk more about matrices in later sections and more about vocabulary, but we may as well get started now. These are the elements of a matrix, and I'm going to take each of those elements and I'm going to multiply it by 1/2. So that'll give me 1, 2, and 7. So my new matrix has the top row, that's the one I replaced, is now 1, 2, 7. The bottom row is 5, -2, -25. That's still the case. Okay. Now, if that's the number 1, I want to change whatever below it into a 0. All right, well, to change things into 1s, usually we want to go ahead and multiply or divide. To change something into a 0, usually we'll want to add or subtract. Here what I want to do is if I take this top row and multiply it by -5, -5 times the top row, 1 times -5 would be -5. So if I then added it to this row, -5 plus 5 would be 0. All right, so let's do that. If I take the top row, that's -5 times the 1, -5 times the 2, and -5 times the 7. And I'm going to add to that the bottom row. I'm going to add row number 2. So I'm going to add the 5, the -2, and the -25. And when I add those, that's going to be 5 and -5 is 0. That's going to be -10 and -2. Add those, that's -12. And that's -35. Add to that -25. That's going to give me -60. So now that's going to become my new bottom row. So that's going to replace row number 2. And my new matrix is now 1, 2, 7. My bottom row is 0, -12, and -60. All right, that's the number 1. And below it's a 0. Now I want to change that to the number 1. All right, well, to change things into zeros, we add and subtract. To change things into 1s, we multiply and divide. So here I want to take this row, and I can multiply by -1/12, or I could also say divide by 12. So it's going to be -1/12 times the bottom row. All right, well, -1/12 times 0, well, that stays 0. -1/12 times -12, well, that's the number 1. And -1/12 times -60, double negative makes that a positive. 60/12 is the number 5. So that's now 1, 2, 7. But now I'm replacing the bottom row with this stuff, 0, 1, 5. And there we go. This is row echelon form. If we now back substituted, that's called the Gaussian elimination method. But now we're going to take it one step further. And you'll remember that there was a more specific form of row echelon, and that was called reduced row echelon. In row echelon, you have 1s along the diagonals and 0s below that. In reduced row echelon, you also have zeros above that. You'll notice that doesn't take much more effort. All I have to do is change that into a 0. So this right here is row echelon. But I'm going to take it one step further. I'm going to take this number and change it into a 0. Once again, to change things into zeros, you add or subtract copies of the number 1 to make it 0. Here, if I have -2 of these, plus that, -2 plus 2 would be 0. So let me take -2 times the bottom row. Let me add to that top row. Well, let's see what that's going to look like. I'm going to take -2 times the bottom row. So -2 times 0, -2 times 1, and -2 times 5. And I'm going to add to that the very top row, which is the 1, the 2, and the 7. Adding the top row. Now, what that's going to do is it's going to change this into a 0. That's what we're trying to do. So that's going to replace the top row, because that's where the change is going to happen. I'm going to replace row number 1. When I do that, well, -2 times 0 is 0, plus 1 is still 1. That's -2 plus 2. Okay, well, that's 0. And that's -10 plus 7. That's -3. Okay, that's fine. So now that's my new top row. So I get 1, 0, minus 3. Oh, sorry. No, that's right. 1, 0, minus 3. And the bottom row I haven't changed. That's going to be 0, 1, and 5. Notice it takes one extra step to go from row echelon form to reduced row echelon form. If you take that extra step of going from row echelon form to reduced row echelon form, this is no longer called Gaussian elimination. This is called Gauss-Jordan elimination. The Gauss-Jordan elimination method, or more commonly just the Gauss-Jordan method, is similar to the Gaussian elimination method. Notice you still have the same person's name, Gauss. Carl Friedrich Gauss is a German mathematician from about the early 1800s, who partially because he was very prolific in writing and doing math, but also because he lived to be a fairly old age. He has a whole lot of discoveries in math. So if you study math, algebra, or higher, you'll run into the name Gauss a lot. In any event, he is, of course, the same person who the Gaussian elimination was named after, and this is just a modification thereof. The Gauss-Jordan elimination method takes one extra step. Notice we could have stopped here and back substituted, but by taking the extra step, it actually doesn't require any more back substituting, because look what this says. This is one x and no y's. Okay, so that's just an x by itself is equal to -3. Hey, that's my x value. This is no x's plus 1y is equal to 5. Okay, so y is equal to 5. Yeah, there we go. There's my answer. So this doesn't even require any more back substituting. Here's my solution. So coming back over here, my solution is going to be -3, 5. And that makes us happy. Now you might be asking, well, okay, but we already saw how to solve systems of equations two other ways. We saw addition method and we saw the substitution method. And I remind you that this basically is the addition method. You say, okay, but if this is basically the addition method, why do we have to write it this way? Well, the main advantage of the Gaussian elimination method or the Gauss-Jordan elimination method is not as apparent here. Where it's more apparent is when your systems get bigger. So for our last example of this section, let's take a look at a much bigger system of equations. Let's say we have 2x minus 8y plus 54z is equal to -4. Notice you now have an equation of 3 variables. So when you're done, you're going to find 3 numbers, x, y, and z. I'm going to say x minus 2y plus 14z, and that's equal to -1. And x minus 3y plus 19z is equal to negative 3. This system, if done by addition or by substitution, would be substantially longer. The Gaussian elimination method or the Gauss-Jordan elimination method, both are roughly the same. They're very, very similar in structure. Once you start having systems of equations that involve 3 or 4 or 5 variables, this method is significantly faster than either the elimination, the addition, or the substitution methods. The other advantage to this is that this, because it appears in an array, in a matrix, because we can write this way, 2, negative 8, 54, 1, negative 2, 14, 1, negative 3, 19, and the augmented column, negative 4, negative 1, and negative 3. Because it can be written this way, you can also use a computer and enter in this array of numbers, and because it requires only 3 types of operations, it's easy enough to program a computer to do this very, very quickly, to the point where if you have something with dozens or hundreds or thousands of systems of equations, the computer can still do it without any problem. But before we can program anyone else to do it or anything else to do it, we got to know how to do it ourselves. So here, I'm going to go ahead and proceed to use Gaussian elimination to solve this system of equations. The pattern is going to remain the same. I want this number to be the number 1, and then below it I need these to be 0, and then I'll move on. All right, so I have a few options. Obviously, one thing I could do is I could just switch rows. But here what I'm going to do is I'm going to divide everything by 2. Why? Because these are all big numbers, but they're all even numbers. So if I divide by 2, my numbers get simpler, and I don't have any fractions. And that sounds like a good thing to me. So I'm going to take row number 1, and I'm just going to multiply everything in half. I'm going to multiply everything by 1/2. All right. So that's going to be, well, half of 2 is 1. Half of negative 8 is negative 4. Half of 54, that's 27. And half of negative 4, that's negative 2. Nothing else has changed at this first step. Like that. If you'd like a challenge, go ahead and pause the video and proceed. It's not going to be anything different, although it does take a bit longer because of how much bigger this is. If you want to give it a try, go ahead, and I will walk you through it once you have finished. All right, so let's take a look. This is now the number 1. So below it, we need to make these zeros. Remember, when you're trying to make zeros, what you do is you add or subtract. And since this is already the number 1, it's easy to just add the opposite of this over here. So I'm going to take row number 1. I'm going to take row number 2 and add negative 1 times row number 1. That way 1 plus negative 1 of these will be 0. And you know what? Since I'm going to do the same thing over here, let me write that down while I'm at it. I'm going to take row number 3 and I'm going to add negative 1 of these. All right, so let's go and do that over here to the side. If I take row number 2, well, that's going to be 1 minus 2, 14, and minus 1. And I'm going to add the opposite of row number 1. So I'm going to add negative 1. I'm going to add positive 4. I'm going to add negative 27. And I'm going to add positive 2. Notice I'm just taking the opposite of all of these. Negative, positive, negative, positive. And when I add those, I'm going to get 0. I'm going to get 2. I'm going to get negative 13. And I'm going to get 1. All right. I'm going to do the same thing for the bottom row. I'm going to take my row number 3, which is made up of 1, negative 3, 19, and negative 3. And I'm going to add to that the opposite of row number 1. So again, I'm going to add a negative 1. I'm going to add a positive 4. I'm going to add a negative 27. And I'm going to add a positive 2. And when I do that, that's going to be 0. That's going to be 1. That's going to be negative is that 8? Yeah, negative 8. And then negative 3 plus 2 will give me negative 1. All right, so just like that. And that's going to become my bottom row. So this first one will replace my row number 2, and this bottom one will replace my row number 3. So let's go ahead and write that out and see what we have so far. The top row remains unchanged for now. The middle row has now been replaced by 0, 2, negative 13, and 1. And the bottom row is now being replaced by 0, 1, negative 8, and negative 1. That's my new second row, and that's my new third row. Okay? So that's the number 1, and everything below it's a 0. What I can do now is I need to change this to the number 1. Now, I could divide this whole row by 2, but that's a fraction, right? If I take negative 13 over 2, that's going to be a fraction or a decimal. And although I can handle fractions or decimals, I'd rather not. Oh, but look, if I switch these two rows, this is a 1, which will come up here. Okay, that sounds like a good idea. So let me take row number 2 and row number 3, and let me switch them. There was nothing wrong with dividing this by 2, but that would have given me a fraction or a decimal, and I would probably rather avoid that. So 1 minus 4, 27, negative 2. Here I'm just going to take this bottom row and put it in the middle, 0, 1, negative 8, negative 1. And I'm going to take this middle row and put it on the bottom. Okay. So now that's a 1, and below it are zeros. That's a 1. So now let's change whatever's below it into a 0. Okay, let me take that. If I multiply that times negative 2 and then add, this becomes a 0. So negative 2 times row number 2 added to row number 3. That's going to replace my new row number 3. All right, so negative 2 times row 2. All right, let's see here. That's negative 2 times 0, negative 2 times 1, negative 2 times negative 8, and negative 2 times negative 1. All of these numbers in the second row. And now I'm going to add whatever's in the third row. So plus 0, plus 2, plus negative 13, and plus 1. So that's going to be 0 plus 0, which is 0. Negative 2 plus 2 is also 0. And positive 16 minus 13 is just the number 3. Finally, negative 2 times negative 1 is positive 2, plus 1 is also the number 3. So that's going to replace my new, that's going to become my new bottom row. So let's see here. That's going to be 1 minus 4, 27. And that's a negative 2. This is now 0, 1, and negative 8. And this is a negative 1. And here that's going to be 0, 0, 3, 3. And now we're just about done. That's a 1, and below it are zeros. That's a 1, and below it are zeros. Now we want to change this to be the number 1. Oh, we'll just divide by 3. So if we take 1/3 of the bottom row and replace that, make that the new bottom row, then we have things in row echelon form. So 1, negative 4, 27, and then that's a negative 2. That's 0, 1, negative 8, negative 1. And here a third of 0 is 0, a third of 0 is 0, a third of 3 is 1, and a third of 3 is 1. And there we go. We have row echelon form, which means that if we wish to use Gaussian elimination method, we can now start back substituting. Or if we want, we can continue to change these into zeros, and then using the Gauss-Jordan method, we could just read our answers straight off. That's entirely up to you, whatever you would like to do. We can continue, or we can just back substitute from here. Here, I'm going to go ahead and back substitute. I'm going to use Gaussian elimination, but of course you can see that you could change these into zeros and get that answer as well. All right, so let me use back substitution here. This is now a system of equations that is related to our original one, but is different. It's got different coefficients. So here, my system of equations is, well, let's see, 1, and you know what I'm going to do? I'm going to write this system of equations backwards. I'm going to write the bottom one first, then the middle one, then the top one. That's just so that I have more space to write. They're all equations, so it doesn't matter what order they're in. So I'm going to write this bottom equation as, well, there's no x or y, just z. So here's z is equal to 1. All right, that's nice. We have part of our answer, z is equal to 1. Now, if I take the second equation, there's no x, just y and z. Okay, well, that's 1y minus 8z is equal to negative 1. Oh, but I know what z is. I can just plug it in. So that's going to become y minus 8 times 1 is negative 1. But now, I can get that y by itself. That's a minus 8. I can just add the 8 over to the other side. And if I add 8 to both sides of my equation, this now gets me my y by itself. Here, 8 and minus 1 will give me 7. And there we go. I found what y is. And finally, I have one last equation. This has an x and a y and a z. Okay, so I have 1x minus 4y plus 27z is equal to negative 2. But I can take my y and my z that I just found and plug them in. So here, x minus 4 times y, well, we know y is 7. Just plug that in right there. And again, we know z is equal to 1, so let's plug that in right there. Plus 27 times 1 equals negative 2. Let's see, that's negative 4 times 7 is negative 28. 27 times 1 is 27. Just like that. And now if I combine these like terms, negative 28 plus 27 is negative 1. And finally, we're done. Because if I add 1 to both sides of this equation, here 1 minus 1 goes away, and we're left with just an x. That's equal to negative 2 plus 1, which is negative 1. And there we go. So we have all three values of our solution. X is negative 1, y is 7, and z is positive 1. So our solution is going to be negative 1, 7, and positive 1. The x goes first, and then the y. Notice here we have a third variable. We have a z. Okay, that's fine. We have x and y and z. All right? So that gets us our solution, and that concludes our problem. And that's the end of our section. So I hope you all have a good evening.